So today we start the last lecture that we have in this semester, and I want to show you today a very interesting method of classical machine learning that is called manifold learning. That's a method somewhere, let's say, in between the machine learning and topology. It's a really interesting method. What can you use it for? So you can use that for data compression. We can use that to reduce the dimensionality. So we all know that there is such thing like curse of dimensionality. And the more dimensions our problem has, the worse will be the result of different minimization methods and so on that we try to employ and to use on this problem. Of course, this method can be used for, let's say, denoising and for visualization of data, because we all know that if we work with some sort of multidimensional data sets, there is a problem that we can show them in, let's say, in 2 or 3 dimensions, because whatever we can draw should have 2 or maximum maybe 3 dimensions. So that's for visualization, and that may help us, of course, do some, let's say, reasonable distance metrics. So that's what manifold learning can do for us. Okay, so a few words about, let's say, mathematics that is behind all these methods. It's not like we need very much of it, but we need some, let's say, notions and some ideas to be able to formulate our problem in more or less rigorous terms. Did you ever study, let's say, topology? No. Maybe you have any idea what that is.
About continuity and all this stuff.
Yeah, so topology is really, that's basically about the continuity. The problem is that when you start, let's say, studying some mathematical objects, you start, for example, with sets theory. So you have some objects, you have some sets, so you basically can collect objects into these sets. But there's a problem to all that sets. They are, let's say, too grainy. So if you are taking a set in your hands, so abstractly speaking, that objects, they will just slip through your fingers like sand. So they are not glued together. So they are just separate objects living in a set. And topology is, in some sense, it allows you to add some notion of how objects can be glued together into something, into one entity, into something coherent. And that is performed with, let's say, notion of adding, how do I say that, some neighborhoods around the points. So you can say that this point is in the neighborhood of that point, and they are in the neighborhood of some different point, and so on and so forth. Of course, there are some rigorous mathematical notions to all of that. So here I have even written for you. So what is basically a topology on X? So you see it's defined in terms of some family of subsets of X. They should have certain properties, and you can say that that defines you a topological space. But just vaguely speaking, you can think about it like you are taking points, and in some sense, you can glue them together into something bigger. And if we consider the notion of topology in, let's say, more details, we can find that topological spaces are very diverse. And in some sense, they contain some spaces that are too strange for us. So we even add some more and more properties to them. So we want them to have some more properties so that we can work with them. And some of these properties, once again, I'm not going into some mathematical details. If you want, you can read all of these. I have written for you some rigorous mathematical notions. But it's in some sense, if you are having a nice topological space, in a sense that every neighborhood of the point looks like a very familiar for us Rn. So we all know what is some Euclidean space. So we live in Euclidean space in some sense, and that's the simplest space we can think about. And if we say that a manifold around each point looks like some Euclidean space, we can think about it like, we can say that it's a really nice topological space, and we can do something with that topological space. So basically, that's a manifold. Of course, there are some certain additional properties to that, but but don't bother with that additional properties. So yeah, here is a nice picture that shows you something about atlases on the manifolds. So yeah, you can define some system of functions that gives you some sort of charts on that manifold, and that can give you something like coordinate system and so on and so forth, and even adding some more properties to that, so you can get into the realm of so-called differential geometry and speak about tangent spaces and so on and so forth. So if you ever study, I don't know, gravity, for example, you will definitely see something like that. So you will work with that manifolds. But for us, that will be enough to think about it like some sort of topological space that locally looks like very familiar Rn to us. And what will be of great importance to us is a strong Whitney embedding theorem that states that any smooth, real, m-dimensional manifold that is also required to be Hausdorff and second countable. Okay, so disregard that. It can be smoothly embedded into a real 2 times m dimensional space. So in some sense, we can think about them as a parts of some multi-dimensional space. So let me try to take a look if I have some sort of so if I have a piece of paper, you can think about it as a manifold that I have embedded into 3-dimensional space. So how many dimensions does it have? Yes, absolutely correct. So that's a 2-dimensional manifold that I have embedded into 3-dimensional space. And we will be concerned with something like that. So we will be having some multi-dimensional space, and in that multi-dimensional space, we will have something like this. Why is this a manifold? Disregarding most of the properties, the first and the foremost thing, if I take any point in here, so if I take any point and I take some neighborhood of that point, so I have a point and I have some neighborhood of that point. So you can think that sitting right here in this point and looking around, I will see this manifold locally as a part of R2. So yes, it has some deformations to it, so on and so forth. It's not like a nice plane. But if I take a very small neighborhood around the point, that will locally look for me just as the plain old R2. So that's basically the most interesting property for us. And what we will be doing today, so what we will be doing, the thing is that all these manifolds, if you are working with some sort of, for example, physical system or something like that, you will be measuring some points in a space, in some multi-dimensional space. And if these points are coming from some sort of, I don't know, law of nature or something like that, or you have some mechanism that is constrained somehow, these points will be most probably lying on some sort of manifold. And what we will try to do, we will somehow try to operate on that manifold to get some interesting information for us. For example, to get that point into some local coordinate system so that we can make the number of dimensions smaller. That will be the first and the foremost problem that we will be trying to solve. And here is an example for you. Suppose I'm having a pendulum. So it's just some sort of mass, and this mass can swing here and there and so on. And if you think about all the possible positions that this mass can have in this plane, you will most certainly say that they all should lie on some sort of circle of radius r. So when I'm measuring positions of this mass, I will be getting numbers. I will be getting two numbers. I will have some coordinate system in here, x, y, and I'll be measuring some numbers. But if I think carefully, if I know what is this system, I should know that just one number is enough to describe its position. Because all the points that I will measure some point here, in here, in here, and so on and so forth. They all are lying on a manifold S1. So I have this one-dimensional sphere, or let's say a circle, and all the points that I'm measuring, they are lying in here on this manifold. And having these points measured, if I have some appropriate methods, I can try to transform their coordinates, that will be basically two numbers, into some sort of one number. So that's what we will be concerned today with. So our manifold learning will give us the ability to somehow transform these two numbers into one number. And the magic of this process is that we don't have any additional information on the manifold on which these points are living on. So we don't know what is the manifold. Yeah, here I have drawn the exact physical system and I know what happens. But in practice, you will be just getting some measured points. So you have data points and that's all. You don't know what's happening in there. So we will try to somehow estimate what is happening right there. So what is that manifold and what can we do with that? Okay. So the first and the foremost motivation of developing all these methods, that was so-called curse of dimensionality. So I have mentioned you before that many algorithms, they work fine, but in low dimensions. And when it gets to some high dimensional input, they become intractable. So that's how it is. And here is some example to remind you of something very similar that we had previously. This is called PCA. So if you remember about PCA, we had a bunch of points and we were trying to perform some sort of transformation of coordinates such that we have most of variability along one of the axes. This sort of PCA transformation is very similar to what we are going to do now. Why? Because all these points, in case of PCA, if they were lying on the perfect plane somewhere in a space, PCA was basically performing what we want to do. So with the manifold learning methods, we are trying to perform something, let's say, philosophically similar to PCA, but with some much more complicated manifolds than just some piece of plane in a multi-dimensional space. So for that case, that was enough just to do some sort of linear transformation, and that was perfectly okay. In cases of some nonlinear manifolds, we will be having some problems and we will need some more powerful methods. And we are going into these methods right now. Okay, so manifold learning is a class of unsupervised estimators that seek to describe datasets as low-dimensional manifolds embedded into higher dimensional space. So here is an example for you. So you have some very complicated manifold. Here we have some points that we have measured, and we are trying with the manifold learning somehow unwrap it. You can think like unwrapping that manifold and getting some lower dimensional data. So how can we do that? In some sense, we can think first of all, so if we have some manifold, so I'm having some manifold and I'm having some points on this manifold, so I'll be having some points, I don't know, here, here, and there. What is the, and I want somehow to unwrap this manifold and transform it into the plane. So I want to take it and make it planar. So put it into the plane. How can I formulate the problem of putting all these points into some lower dimensional space? How do you think? What should I do? What should I require? So all machine learning methods, that's minimization or maximization of something. How do you think? What can I want to minimize or maximize in this case?
If we're talking about classification, we shall pay attention to the distance between points so that we can like group them into some clouds, let's say, in high dimensional clouds. And in that way, if we are transforming from a very high dimensional space to a lower dimensional, we need to somehow maintain that notion of distance between points themselves so that those, let's say, quote unquote, clouds in higher dimension will correspond to somewhat similar clouds in the lower dimension.
Yes, absolutely correct. Really nice. So if I'm having some points on that manifold, the first idea that I can come up with, so I have some distances between these points. So why don't I try preserving these distances when I am squeezing it into some plane or some lower dimensional space? So basically, why not? So I have some distances between them, and I want to preserve that distances. Of course, I can do that perfectly. Well, I can do that in case if points are lying on some sort of hyperplane, and for example, PCA will do that for me. But if I'm getting to some nonlinear manifold, that's all. I can do that basically. But at least I can try to preserve them as much as I can. So at least I can try to do that. And we will see that all our methods are basically trying to do something in that direction. So we will be trying to preserve some distances and unwrapping our points, squeezing them into some sort of smaller dimensional space. Okay. Once again, we start with some sort of test-driven development. So let's look at few test cases that are often used to test all these manifold learning methods. The simplest case, of course, the plane. So if I have a plane in some multidimensional space, I'll be expecting that this plane will be transformed so that I have just x and y coordinate in that plane. So some sort of linear transformation that, for example, PCA can do for us. And of course, our more complicated methods should be able to handle these cases as well. So that's what expected. What else? Two more test cases like S-shape and Swiss roll, so spiral. So once again, we have a bunch of data points, and these data points are generated such that they all live on one of these manifolds. So if you have manifold, and here we have many points. So what we'll be trying to do, of course, we will expect that if I have some sort of S-shaped manifold, so it is deformed somehow, I will expect that my method will take these S-shaped manifold, and it will try to unwrap it and make it more or less planar, and once again put it into the plane so that we have only two coordinates, for example. Here is the side note for you that like Swiss roll looks in real life. So probably you might guess that this sort of manifold is really looks like this real life Swiss roll. And one more side note for you, we'll be seeing today many interesting pictures, and you might think about them like created in a style of pointillism. So here is an example of such a pointillistic picture for you. So that's Paul Sagnac. And we'll be seeing today many pictures that basically look like this sort of art. Okay, let's go further. Let's take a look at few of the manifold learning methods and how do they work. Here is the data set I'll be using throughout all the lecture. Basically, this is how this data set should be looking when it's not lying on any sort of manifold. So what I'll be doing, so I have some points in 2D, and here's how they look like. Now I will take these points to different manifolds. So I will take some sort of manifold, and I will just set these points on that manifold. That may be S-shaped figure, that may be Swiss roll, that may be something different, so that depends. Then I will pass that manifold with all these points into the method that should reduce the dimensionality to 2. And of course, what I'll be expecting, well, in a perfect case, to see something like this. Of course, I will not always get something like this, but I will be expecting. And one more thing for you, let's say, to appreciate all these methods, when I'm passing points to all that methods that I have and that I will show to you, they don't know anything about color of these points. They will not have any information on that. These colors are just for us to understand how these points are situated in a space and what is going on with their relative positions. So methods will be just getting some numbers, some coordinates, and transform that coordinates. Now I'll be taking colors together with that transformed coordinate, so I will apply colors to transformed points, and we will try to look at that transformed points and to appreciate whether the method has preserved the relative positions of the points or it did not. And here is a bunch of different methods for you that we have in sklearn. This is the original manifold. So I have taken all my points and I put them on this sort of S-shaped manifold. If you look carefully, you can see that here we have letter I, here we have a heart, and here we have K, A, and Q. Yeah. So that's basically my original points, but they were transformed into this sort of S-shape. And now I'm passing these data to different methods that I have in sklearn. We will consider some of them just in a few moments, and I will show you what is the math behind all that methods. But here I want you just to appreciate how they work. So here is just plain LLE. You see that it was not very, let's say, successful, but you still can see some structure in these points. So they are not like just mess around randomly, but still some structure is preserved. Here you see LTSA, or Hessian LLE, or modified LLE. And if you look carefully, you can see that the structure was basically preserved. So the points that were close to one another, they are still close to one another. Here is isomap. Once again, it was, well, not very, let's say, perfect, but still some structure is seen, so it has preserved some structure. MDS was not able to handle with that spectral embedding as well. And TSNE, well, wasn't able as well. Of course, they work with some different manifolds, but that's what we have at the moment. So you see that there are a bunch of methods in sklearn, and at least some of them are really nicely reconstructing almost the original image that we had. And we see that the points that were close to one another, they are really close to one another after the transformation. Okay, so today we will consider three methods. So multidimensional scaling, MDS, locally linear embedding, LLE, and isometric mapping, isomap. So that's the three methods I want to consider today. So let's start with the simplest one, MDS. So MDS can be, well, subclassified to classical metric and non-metric. We will consider so-called metric MDS. So the idea is to minimize so-called stress. So what do we have here? So in metric MDS, we are seeking for a map. Here is the map from some multidimensional space to a space of lower dimension. And we want that pairwise distances between points are more or less preserved. So we are returning to the idea we had at the beginning of the lecture. So we have some points in some multidimensional space. They are living on a manifold. And I want somehow to preserve the distances between these points. So we introduce a distance matrix that describes basically distances between all the points that we have. And here is our stress. So that's what we are trying to minimize. So what do we have? We have a distance matrix for the points in a higher dimensional space. We have distance matrix for points in lower dimensional space. So after transformation, we have performed these two matrices. They have the same number, let's say, of rows and columns, because their number of rows and columns is basically the number of points. So of course, number of points does not change. So you can subtract them and you can calculate this sort of norm squared. So it's sort of Frobenius distance between matrices. So you can do that. And if you have this parameter, you have stress, you can try to minimize that and find such a transformation, such a new coordinates y, because coordinates x, they are fixed, that's given, that's our data set. You are trying to find coordinates y such that you minimize this stress. This can be done numerically. The procedure is called stress majorization and can be performed with different algorithms, like, I don't know, some Crossco or some different approaches. That's okay. Let's try to use MDS on some of the data sets. So here is the simplest data set we can think of. Here are our points, and I have just placed them on a plane in a three-dimensional space. So now each of these points has three numbers as its coordinates. Now I try to perform MDS. Performed very simple. In sklearn you have manifold. You are doing manifold.mds. defining the number of components that you want to have. And all in all, this is the result that we get. So we see that MDS is able to handle the problem of a plane. So if we have a plane in three-dimensional space, it's perfectly able to put that into the two-dimensional space. That's really nice. Of course, you can do that in some more dimensional spaces. So if you have some multi-dimensional space and you are trying to reduce the number of dimensions, MDS will perfectly handle all the linear manifolds if you have them. If we are having a nonlinear manifold, what happens? Basically, in some cases, MDS will work. In some cases, it fails. So now I want to show you a case when MDS will fail. Here is an S-shaped manifold. So once again, you can look at the points. You see the structure in these points. And now we'll be trying to unwrap these S-shaped manifold, put it into the plane. But we want to do that with the MDS method. So what happens? Here is the result that we get. Now you can see that S was not unwrapped, unfortunately, so we don't have what we want. Still, some structure is preserved. So if you see the colors, you see that they are not like somehow messed. So some structure is preserved, but it's not that structure that we wanted. So we wanted something a little bit different. And what do we do with that? We need some new method. So we need some new method to perform something with some highly unlinear data sets and even with this sort of S-shaped manifold. And how do you think? What ideas can we employ? What can we do better with MDS to make it work with these sort of data sets, like S-shaped data set or something like that? So what can we modify?
Kind of kernel to move even higher up in dimensions
Mm-hmm.
and come to the device error and with the height.
Well, interesting idea. So I'm not sure if it's implemented somewhere, but sounds quite interesting. What else can we think about? Basing, for example, on some sort of properties of the manifolds that we have. So
You idea or some kind of system.
So what is the main problem of the MDS? How do you think? So what goes wrong? Why it's unable to unwrap that S-shaped manifold? Yes, it's nonlinear, but what does MDS do? So you have some points on the manifold, you are measuring distances between them, and you are trying to squeeze everything into the plane but preserving that distances. What can go wrong with the S-shaped manifold? It's folded, it's manifold, yeah. So it's folded. And if you have some point somewhere in here, for example, and you have some point in here, so what happens? On the ends of that S ladder.
They are closer to each other than they should be.
Yeah, they are much closer to each other than in some sense they should be. So I'm having this distance in my distance matrix between this point and this point. This distance is quite small because my manifold is somehow folded, so they are close to each other. And when I'm trying to unwrap that, I should make that distance from being very small to being very large. And of course, it resists. It resists because it adds me some big error to the function that I'm minimizing. So that's my problem. So we should try to do something with that distances. And it so happened that in one, let's say, volume or in one number of a journal Science on December 22 of 2000, there were published two articles that were solving the problem of MDS in two different manners. So that's really rare thing to happen, but in the same number of the same journal, we had two articles that are at least trying and that are solving this problem in two very different manners. So one article was introducing so-called locally linear embedding, LLE. The other one was introducing isomap. And let's consider both of them and what people have done to make these methods working and what were the ideas. LLE is based on a simple geometric notations. And suppose you have your data consists of n real valued vectors xi. Each has dimensionality d sampled from some underlying manifold. And provided there is sufficient data, so you have many points, and the manifold is well sampled, we expect that each data point, its neighbors, they lie on a close to a locally linear patch of the manifold. So what have I told you on the beginning of the lecture? So the defining property of the manifold, well, if we forget all the rest, the most important for us property of the manifold is the fact that it's locally looks like some lower dimensional space. And if we have many points on this manifold, if I take a small neighborhood of some point, I can think about this point and everything that lies in that small neighborhood of that point, like living in some smaller dimensional space. And I can take that neighborhood to that smaller dimensional space just with some sort of linear transformations, like I did with the PCA. So I'm having some part of plane locally. And that was the main idea that got rise to the LLE method that we are considering. We don't want to consider all the distances on the manifold. We want to work with some small neighborhood. So I'm taking a point, I'm taking its neighbors, and I'm saying, well, this point and its neighbors, they live in a small patch, in a small neighborhood that looks like locally some smaller dimensional space. And I can perfectly transform that thing into some smaller dimensional space. Of course, I need to do that with all the small patches I have on the manifold, and of course, I need to add some conditions to make everything work together. But right now, the things are getting better. Because, well, let me for a moment skip this part, because if this is what we had in MDS, here you see all the distances that we have. And of course, we can expect that distances between this part of the S-shaped manifold and this part of the S-shaped manifold, they are creating large stress when we are trying to squeeze everything into the plane. And they are basically making our method non-working. And here is what we get if we consider LLE. we are considering just distances to some closely related points. We are working with some small patches, and here we don't have that periodic distances that we had in MDS, and we can try to unwrap this on a plane. So here is the general idea of the LOE that makes it working in the cases like these S-shaped manifolds. Okay, so what about the mass? We are trying to characterize the local geometry of these patches by some linear coefficients that reconstruct each data point from its neighbors. We are trying to play around with that idea that this small patch is basically some sort of is linear. Suppose the data lie on a near to smooth nonlinear manifold of lower dimensionality. To a good approximation, then, there exists a linear mapping consisting of translation, rotation, rescaling, that maps the higher dimensional coordinates of each neighborhood to local internal coordinates on the manifold. So by design, the reconstruction weights W reflect the intrinsic geometric properties of the data that are invariant to exactly such transformations. So therefore we expect the characterization of local geometry in the original data space to be equally valid for local patches on the manifold. And here's how it works. So here we have a part of a manifold. I'm taking some point and I can search for its nearest neighbors. So I can define the number of nearest neighbors I want to search for. So that's a hyperparameter that we give to the method. I find these nearest neighbors, and I'm considering this small linear patch. So here you see a few such patches shown to you. So we consider that to be linear when the overall manifold is highly nonlinear. Now, what can we do? We are trying to describe that point that we have taken in the patch like a linear combination of coordinates of all the rest points. So if they are lying on a plane, that should be possible. And having that parameters, we are trying to do the same on the plane where we are projecting everything to. Here is the algorithm. So first, you find k nearest neighbors, you solve for reconstruction weights, and you compute embedding coordinates using that weights. Now we have to minimize, let's say, basically 2 loss function instead of 1. But anyway, that works. On step 2, if we are solving for reconstruction weights, so here is what we have. So here's our central point, xi. These are xj, these are the points from that small patch that we have taken from the manifold. And these are some sort of weights we don't know. And we are trying to search for these weights in such a manner that the result is very close to the point xi that we have. So we are trying to express every point in terms of its neighbors. So that's what we have. You can think about it like, I don't know, like putting a point on a plane and drawing some small vectors to all the rest points. And if you think for a moment, you will definitely find out that, yeah, it should be possible if your points lie on some sort of plane. And in a multi-dimensional space, that will be okay as well. So we have a linear patch, and we should be able to do that. So that's what we have, and here we get all these weights. We add some additional restriction, like all the sum of the weights should be 1, so that's okay. If you have seen some sort of, I don't know, barycentric coordinates or something like that, that should be quite familiar for you. This is what we have. So we get this W. Now we have all these W. What do we want? We want our points to be squeezed into the plane. Now we are saying I want my W's to be conserved. So this means that I want to minimize the different loss function phi of yi, where yi are points in some smaller dimensional space. So I'm putting them into the plane, and now I'm using these weights I have calculated on the previous step. So I have these w's, and I'm searching for positions of the points for y's such that they minimize this sort of discrepancy between the point and its neighbors on the plane. All in all, what do we have? So I have points in some multi-dimensional space. They are living on some sort of manifold that can be highly nonlinear. So I don't know, something very, very strange. I'm taking each point, I'm taking its small neighborhood. In this neighborhood, there are some different points living. So it has some neighbors. I'm describing this point in terms of its neighbors, in terms of some linear coefficients that give me this point. And I'm saying if this thing looks like some linear patch, and it should look like because we are working with a manifold, if I put that into the plane, I should have there the same patch as well as I had in my highly dimensional space. That means that my coefficients W that I had when I was describing this point in terms of its neighbors, they should be preserved. And now I'm trying to search in the plane for such points that preserve my coefficients W. And if you remember our previous methods that we have considered, it's not a big deal that we are minimizing two functions. We just do that, let's say, step by step. Minimize one, minimize another, minimize one, minimize another. So nothing bad happens. Okay, so what is LLE in essence? So in essence, LLE is some sort sum of local MDSs. So if I'm looking at each patch, I'm basically performing an MDS. So I'm having some distances to different points, and I'm trying to preserve them. And this is the LLE. And now you might guess, since LLE is not considering all the distances, but just local patches, we have much more chances to unwrap this S and to put it into the plane correctly. Yes, I guess there was some question.
Yeah. Can I ask, can I please return to the formulas?
Yes, please.
Why distance is squared here? Is there any mathematical reasoning behind it?
You mean why do we use squares in here?
Yes.
Well, we use squares almost everywhere because this is a nice function. We can try to use something, I don't know, like absolute value, yeah, so or some norm. But in most cases, these functions may not have some, let's say, derivatives. So if we are working in Euclidean space, we will have all that square roots and so on and so forth, and they just don't look nicely. So in many cases, we use just squares. But probably you can use some different measure of discrepancy between the points. So that's the same as we had, for example, considering, I don't know, linear regression. So we were using squares there as well, just because square is a really nice function, and that gives us something nice and convex, and it's much easier to optimize with different methods than if we use all that square roots and get some points where we don't have derivatives and so on and so forth. But it's not like you should use square. You can try to use some different measurement of discrepancy between points, and maybe you will get something even better. Who knows? But what we do always, we are trying to use the simplest thing that we can, and that will work. So in this case, I guess that squares are really the simplest thing that we have.
Thank
you. Okay. Here is an example of usage LLE on the S-shaped dataset. And you see that really it has unwrapped everything perfectly. So that's really great. So all the points that were close, they remained to be close. So that's really nice to have. Isomap, the other approach to the problem with distances that we have. So when we were considering MDS, we know that there are too many distances, and some of them it's really not good to consider. So LLE was trying to fight that with just removing at least some of the distances. What does the isomap? The isomap goes the other way around. So it says, well, if we don't have really nice distances like distances in Euclidean space, so just measuring distance between 2 points on some highly nonlinear manifold is not good, because these points may appear close in a multidimensional space, but they should be far away when we unwrap everything. Then it says, okay, we should find some more correct notion of the distance between points. And it tries to do that by finding distances on the manifold, let's say on estimating the distance that we should have on the manifold. And here is an example for you. Here is the Swiss roll. And if we have our points on that manifold densely packed, so they are dense enough, we can try to estimate the distance along this manifold. You see this blue line, that's the real distance that we should have if we unwrap everything on a plane. This line shows you the distance that we will have if we calculate that with MDS, so just distance in Euclidean space. And here we are trying to get some estimate of the real distance by getting from one point to another, but we are moving between the points on the manifold. So here is the manifold unwrapped. And if we are trying to move between points in such a way that we are trying to find the smallest distance along that segments, so from one point to another, so I'm moving from one neighbor to another and so on and so forth, so I'm moving in some small segments. And from that segments, I'm trying to make some sort of curve from one point of interest to another. And here you see in red such a collection of segments, and you might see that it's more or less close to the blue line that is the real distance on the unwrapped manifold. So what we are trying to do, we are trying to fix the notion of distance by not measuring that in the ambient Euclidean space, because we know that's maybe no good because we have some highly nonlinear manifold, but we are trying to measure that along the manifold. But since we don't have the manifold itself, what we try to do, we say, okay, suppose our points are really densely packed on that manifold, and we can try just to move from one point to another to get from A to B, and that will be our estimate of the real distance on the manifold. And when we are doing these sort of estimates, of course, we are expecting to get something better, because now we don't have that small distances that will introduce some enormous strain into our loss function. Now we will have these distances much better, and we can expect, of course, something much better. So what do we do in this algorithm? So we are trying to construct a neighborhood graph. So we are taking some number of neighbors and we are trying to create some graph. In this graph, there will exist some sort of paths. So we are trying to compute the shortest path between 2 points A and B. And when we have computed that shortest path, now we can estimate the distance between A and B and use that distance in MDS. So instead of that Euclidean distance, we will try to use this much better distance. Isomap is basically MDS with some sort of geodesic distance. So once again, if you will ever study, I don't know, gravity or something like that, you will most certainly see some sort of geodesics, and you will know what that. So MDS with geodesic distance, and what we are trying to do is some sort of geodesic distance. It's an estimate of the geodesic distance on the manifold. And then we are trying to do that MDS. And here is the result. And you see that that Isomap is able to perform that unwrapped. I see we have a question here. Yes, please.
Yeah, what will happen if we have not one S-shaped like figure in our dataset, but multiple of them, but they're at significant distances relative to each other and probably like different angles and with different scalings? Will it handle it, or it should be somehow separated and we should apply Isomap or previous LE algorithm separately to each of them? LLE should handle it by design, but will Isomap handle it?
I guess it should handle that. Well, yeah. So you mean that we don't have one connected component, but like few connected components?
Yes,
so
yes.
Like data is living on few separate manifolds. I guess it should be able to more or less handle this thing. So why not? I didn't try that on my own, but I think that should be okay. So it will handle just one manifold, the other one, and maybe some closest points of that manifolds. They will, I don't know, either see each other or maybe they even won't see each other. So why not? If I'm creating some neighborhood graph, maybe none of the points from the different connected components will fall into the neighborhood graph of points from the other connected component. Yeah, that.
Well, it's probably the problem with all of those approaches. If we have two manifolds that are separate but close to each other, they get connected.
Well, maybe yeah. So that depends. But if the distance, if they are far apart, why not? If they are close enough, that's the same problem if we have one manifold, but it's really nonlinear. If I'm getting my points very, very close to each other, so how can I separate something like this? So I can separate some things that are, well, separated with some distance. But if distances between points on the manifold itself become, let's say, significant or comparable to the distances from some parts of the manifold, then probably I will have some troubles with all these methods, because how can we estimate that?
Probably can right? Because the number of neighbors they are connected to them.
Yeah, the number of neighbors really influences heavily the results, so that's right. But anyway, if we have distances between points on the manifold comparable to the nonlinearities of the manifold, we are anyway in trouble, because even if you look at these points, you just eyeball them, you will probably not be able to say if there any pattern in that points or they are just some sort of scattered all around the space. So to see some pattern, we should have some, I don't know, some reasonable density on the of the points on the manifold. We are not seeing the manifold itself, we are just seeing some points. So if we want to see, for example, some nonlinearities of that manifold, we should have enough points to be able to pinpoint that nonlinearity. If I have, for example, some, I don't know, some 2 or 3 points, I will be not able to say is that a plane, for example, or is some sort of, I don't know, some sinusoid, for example. So who knows? If I have enough points, then that will be okay. Yes, please.
Yeah, but what if we have enough points, but for example, if we have like word vectors, word embeddings, and there is like this high dimensional space, so these embeddings, I'm not sure whether we can apply any manifold learning method here, because it's just my assumption, because this space looks like it's there is high variety and okay, my question is there any measure of how likely is that points can form a manifold, or they're more like something else, like some, I don't know, just is there something opposite to manifolds, like of how points are placed in the space?
Like supposing that points come from some manifold, it's not like a big assumption. You almost always can suppose that they lie on some sort of manifold. The very different thing is that can we do something with that information? So can we do something with that? Can we reconstruct somehow the manifold and so on? So that's the different problem, and I guess you can just try that in practice, and I'm not sure if we can have some beforehand some ideas whether it will work or it will not work. Of course, in highly dimensional case, when we don't even see that points and we don't have any ideas how do they look like. So the assumption itself that the points come from some manifold, it's a not very big assumption. You can think about almost any points that way, so it doesn't restrict you by any means. The other problem is, can you do something with that manifold? Do you have enough points to, for example, reconstruct it? Do you have enough information, or is these manifold good enough so that you can somehow put it into smaller dimensions or something like that? So that's
what if we have
problem.
Oh, sorry.
Yes, please.
What if we have like three-dimensional space, but we have two spheres? I mean, or balls, so there is something inside of them as well. And then we use manifold, like two spheres, they're separate. And we apply manifold learning, and what we'll get as the result.
Well, it's hard to say so beforehand, so I guess I should try that on my own. So probably that will depend on the distance between, on the difference between radii of these spheres. So if you have a big difference between radii, so maybe with these things like MBS and so on, you'll be able to get just two separate components in different parts of the plane. So you will not have neighbors from one to another. If they are close enough, you will probably get some mix of points from one sphere and the other sphere. So, but that's, I don't know, just my guess. So we should just try that to see what happens. Because you should know that when we are doing manifold learning, of course, we are neglecting something. And one of the areas to use manifold learning, well, as any dimensionality reduction, is when we are trying to deal with noise. So if I have, for example, some sphere and I have points on that sphere, but these points are not perfectly aligned with the sphere, but there are some, I don't know, some epsilon that they are fluctuating all around the surface of the sphere. And when I'm doing manifold learning, of course, I'll be expecting to somehow unwrap that into the plane, despite the fact that unwrapping a sphere into the plane is a really big problem, because you know that you can't just put it into the plane. It does not work that way topologically. Probably you will have some problems even in this respect. But anyway, you will try to disregard that small epsilons. And if you are having two spheres quite close to each other, so how do you know that's some sort of noise or it's some sort of regular pattern? So that will
And
depend on the parameters and so on. Yeah.
can we somehow visualize, like see, before like the points are projected onto some smaller dimensional thing, can we see how our algorithm sees like the underlying manifold in our initially highly dimensional space? For example, we have three-dimensional space, we have this S-shaped figure, and we have data points on that. Can we see like the manifold in that three-dimensional space before it gets projected onto two-dimensional plane? Because I just don't know which primitives are used under the hood, what exactly happens, how exactly projects it, all the stuff.
It's not a problem for three-dimensional space, so I have already showed you at least a few pictures of that. But the problems start when we are getting promoted to some higher dimensional spaces. So we can perfectly draw 2 dimensions, we can draw something about 3 dimensions, but what can we do with 4 dimensions, for example, or 5 dimensions? And we should remember that our data points, it's what? That's collection of features. And in many cases, we have a lot of features. So if we are considering, I don't know, some sort of picture, you will have a feature connected to each pixel of that picture. So that's enormous amount of coordinates, and that's a very highly dimensional space. So the problems start with 4 and more dimensions because we just can't draw them. And we know that as humans, we are restricted to with, I don't know, with whatever we know to 3 dimensions. So we live in a 3-dimensional space, and we basically have no idea what can happen in 4 or 5 or 6 dimensions and so on. So it's just outside of the abilities of our mind. So that's the basic problem that we have.
Yeah, sure. But I meant like in the case of 3D, you show us like with the visualization of
Yeah, in 3D, that's perfectly okay. You can draw your
Uh-huh.
data set, you can look at it and maybe do some guesses of what parameters do you want to choose and so on. That's perfectly okay. So nothing prevents you from that. But the problem is that most practically interesting cases, you'll be having much more than 3 dimensions. So I use
but
them. Yeah, please.
does the algorithm like at some step generate a mathematical function that some figure that I can draw and see the approximated manifold in like initial space, for example, three-dimensional space? So you showed us like the ground truth manifold in three-dimensional space. You showed us data points. You showed us visualization of intermediate step, which involved like construction of distances. Um, and you showed us the final result on a lower dimensional space. But
Yeah.
does it generate like some equation that we can calculate and like calculate different points and show it like the approximated manifold in the initial space?
We are just, let's say for the MDS, for example, we are just calculating the matrix of distances. I don't know. So maybe you can visualize the distance matrix, but I'm not sure if that will give you any, I don't know, interesting information on that manifold. So I'm not
Okay,
sure
okay,
if you
thank
get
you.
something from that. So we are basically working with numbers like all these distances, and I'm not sure if that's helpful. But yeah, you can try at least visualize that. Maybe that will tell you something. I'm not sure.
Can I also ask a question?
Yes, please.
When we are using this geodesic distance, how we searching for closest neighbor? So we taking like closest point, then some closest point to that point, and are we restricting somehow this amount of closest points, or or we are using additional Euclidean distance to filter those to not go too far with neighbors?
We are restricting the number of neighbors, and the neighboring points we are basically catching with the Euclidean distance. So let me draw that for you, maybe if you wish. So for example, let's say this is the part. Oh, this one. So this is a part of my manifold. It lives in, for example, a three-dimensional space, and I'm having some points on these manifolds somehow scattered around. So for example, I'm taking this point. I can calculate distances to all the rest points, and I can find, for example, I don't know, 5 closest points to this one. So I'm supposing that whatever we have, so once again, the defining property of the manifold, despite all the rest, and the most important, let's say, for us, was that it locally looks like some smaller dimensional space. So that's why if I take closest points, I can calculate Euclidean distances, and I can suppose that these Euclidean distances are not far enough for being the true distances on the manifold. Because I suppose that small local patch, it should look like some smaller dimensional space. So for example, if everything lives in R3, I may suppose that this thing lives in R2. So I'm just taking some point. I am looking for, let's say, for all points that I have around this one. And I'm taking, for example, here 1, 2, 3, 4 points that are the closest to this one. And I am creating, let's say, edges. So I'm basically creating a graph. This will be my edges in this graph. And with each of these edges, I can associate a number that is Euclidean distance between these points. And that's good enough because I can suppose that in a local neighborhood of this point, everything is linear. If I take a different point, let's say this one, I can once again look around. I can check for closest points. Let's say this one, this one, this one, this one. And once again, I'm creating new edges, and I am adding some numbers to that edges that signify for me the distance between this point and, for example, this point, and so on. I will do that with that small patches. I will do that with all the manifold I have, with all data points I have. And at the end of the day, I will transform whatever I had in here into some sort of abstract graph. So I will have some points. For example, this was point P. I will have point P. This was some Q. I will have some Q. And I will have all the different points all around. And they will all be connected with some sort of edges, some edges, so on and so forth. And now if I have this sort of graph, and I know that I'm interested in, for example, distance between this point A and some point in here B, and I'm having all that edges all around the place. So I don't know, I'm drawing them more or less randomly right now. I can try to get from A to B, to get the smallest distance from A to B, just by moving all along these edges. So there are algorithms that allow you to do that. For example, I don't know, maybe some Pascal algorithm or something like that. So you can try to take from this graph to find some sort of tree with that smallest distances from A to each point, and you can calculate all the distances, and of course you will get distance from A to B as well. So that's pretty easy, I guess. So that's what we have. So we are transforming this into some abstract notion of graph. We are endowing the edges with distances that are basically Euclidean distances, but with the points that are close enough, that are in close proximity to one another. And then when we have all this graph, we can calculate distances between points A and B just by moving along the edges of the graph.
So construction of the graph requires a lot of resources, like or not if you have a lot of points, and
well,
could be this a problem?
You will need to calculate the whole distance matrix. So as in case of MDS, we should calculate distances between all the points. We will need to do the same in here to find some nearest neighbors and so on. So yeah, I guess that's at least n squared complexity. So at least to get some idea of these points. So yes, these methods, they are quite slow, let's say. So you probably, I'm not sure if you'll be able to use that on a very, very large data set. So probably you will have some troubles in there. But that's what we have.
I understand correctly that if we use like linear patches, those this is isomap, yeah, but linear patches like more local. So or not? Like
we are anyway using the idea of that locality. In case of LLE, we use that directly just by working with these sort of patches. In case of isomap, we use that indirectly by supposing that distance between neighboring points is approximately the same after we transform manifold into, let's say, into the plane. So anyway, we use that manifold should locally look like some smaller dimensional space.
Yeah, but LLE won't be like faster, yeah, because we also need to calculate all the distances. Yeah.
In LLE, we will need to do the same. How do you know which point is close to this one and which lives in that small patch if you don't calculate all the distances?
Okay.
So you should somehow find out which points are close and which points are not close, let's say. So maybe you can do some sort of optimizations, but you can do the same thing in here. But there's the problem. So you have just a bunch of points that are not structured in any way. And you should somehow take one point of there and say, well, that point, and that point is a neighboring point of this one. And that's a really complicated problem because we have, even for large data sets, there are some separate algorithms for searching nearest neighbors approximately. So the things go into, so the problem is so that we even in some cases, we can't even use some conventional algorithms, and we are getting to searching for some approximate nearest neighbors because we have too much data. So maybe you can find that, for example, if you use some, I don't know, a phase library. Have you heard something about that? No? So you can check that. That's library developed by Facebook, and you have a lot of functions in there to search for nearest neighbors approximately. And it's really widely used when you are doing something with some large data sets, some large databases. So you are absolutely correct in a sense that, yes, we have a performance problem. With the conventional algorithms, I guess we won't be able to do something because we should check distances between all points to understand who is closer and who's farther. So I can't guarantee without checking all the points that there is no point in here that is closer than all the rest points. And in some cases of large, very, very large databases, people even get to some approximate search for nearest neighbors, and they say, okay, we are ready to the fact that we don't get the exact result, or it's not very good, but we are okay, or we get some result with some probability, but we are okay with that because we have so much data that we are not able to do something with that. So yes, that's the problem. Okay. Okay, so let me show you some demo and some small example. And I guess with that, we'll be able to wrap up. So it's probably. Okay, what do we have? Okay, hopefully this code works. I'll try to start that. Okay. Or somehow doesn't. Why not? Okay, something.
It's a bit slow, like wait 5-10 seconds.
Yes, you're right. You're right. It's just really slow. Okay, so you're right. Yeah, that's the first one, I guess. So a plane, and I was trying to do something with MDS. Okay, let's try to do something with S-shaped region with the LLE. So here is the number of neighbors. Let's take 10, for example. I'm not sure how that plays out. So this is some sort of example that shows you a few different manifolds. So you see here a Swiss roll, a cylinder, helicoid, cone, and even a Mobius strip. It's a really complicated thing because you can't put that into the plane exactly, so you will always get some sort of artifacts from that. Okay, so I guess it's working really, really long, yeah? Let me try to restart that once again, maybe. Not sure why that works so long, because previously everything was more or less okay. Good. While it starts, let me show you then some different example. Here we have images of faces, some small data set, and in these data set we have a little bit more than 2,000 of images, and each has almost 3,000 pixels. So if we consider each pixel as a coordinate, we are basically having each of these images as a point in a 3,000 dimensional space. now what we are trying to do, we are trying to perform some sort of isomap on these data set. So we have the data set of the pictures, and I'm performing isomap, and I'm trying to squeeze everything into 2 dimensions. And here is some sort of result that I get. Well, looking at these results, what can you say? Do you see any patterns in the result that we have in here?
Yes, horizontal
Darker
axis
face is right.
brightness.
Right side. Yeah. And whiter guys on the left.
Yeah, so you're right. So we have overall brightness of the photo changing from left to right. If photo is brighter, you have it more likely to have it on the left. If photo is a bit darker, so it's more likely to see that on the right. So the overall brightness is the coordinate x. But now if you look along the coordinate y,
The direction where the face looks.
yeah,
Opposite.
you're right.
Right.
The images on the top side, it's more, let's say, probable that the face looks, for example, to the right. And if you are looking on the images on the bottom, so when y goes down, it's more probable to see a face looking to the left. So that's what we have. And what I want you to appreciate in this example is the fact that the manifold learning method knows nothing about faces. It doesn't know anything. It's just a point in a highly dimensional space. I don't have any face detector in here. I don't have any, I don't know, neural network that understands where are the eyes or the nose or whatever. So nothing is known about the underlying meaning of that coordinates of the point. It's just a point in a highly dimensional space. It could have been, I don't know, some temperature, pressure, and something else in that data. And it's still able to find some structure in there. I guess it's a really nice example of the case of really highly dimensional data, and that manifold learning allows us to find some patterns in that data. We cannot imagine, of course, 3,000 coordinates. That's too much. So I cannot draw these points. I don't have any idea how do they look like in that multidimensional space. But the isomap was able to get some information from there, squeeze everything into 2 dimensions, and we see that this information is even somehow meaningful, despite the fact it does not know anything about the internal structure of the data and what do we mean that these are some sort of faces. It could be cars, it could have been anything basically. And the other one example I want to show you, it's our beloved data set MNIST, some numbers, some handwritten numbers, and we are doing something with that numbers. And in this case, I want to show you isomap on that numbers. So here with colors, you see different digits, and everything is squeezed into 3 dimensions in this case. So once again, if I have a picture of a digit, that's a really highly dimensional space. I guess these images, I'm not sure which MNIST I'm using. There are at least 2 of them. One contains images 8 by 8, so that's 64 dimensions, and the other one contains 28 by 28. So I'm not sure which one I used here. But anyway, it's many dimensions, even in case of 64 dimensions, so that's quite a large number. And if I squeeze everything into 3 dimensions, that's what I have. And you see that data points are somehow grouping together, which makes them a better candidate for using some, I don't know, some different methods on them to separate these points, to clusterize them, to perform, I don't know, some sort of classification and so on. So using this method before any other methods, like something for classification, I don't know, some SVM, for example, can make the result of that other method much better. Because we see, even with bare eyes, we can see here some sort of structure in this data, and the number of dimensions is now quite low. So just 3 dimensions, it's really good to work with. And here is example by squeezing everything into 1 dimension. And here I'm showing you the number 1 that was squeezed into 2 dimensions. And once again, you can look at this and you can tell me whether you see any patterns in this image.
Well, from left to right, it's the direction.
It changes direction. If we have some picture on the left, it's more probable that the person was writing 1 from the upper right corner down to the lower left corner, yeah? And if we see the image on the right, it's more probable the other way around, yeah? From the upper left corner to the lower right corner. Yeah, so that's right. And you see that the angle when we are getting to the bottom, this number 1 gets more straight. And moreover, you see that here is some sort of island of 1s that were written, let's say, in a more fancy way. So it's not just some sort of 1 stroke, yeah, but here you see at least 2 or even 3 strokes when you are drawing this 1. So that's what we have. So there is, once again, there is some internal structure seen in here in 2 dimensions. And once again, the method does not know anything about what are we feeding into it. So what is this data? It doesn't know that this is number 1 or this is number 2. It doesn't even know that this is a picture. So it could have been anything, some collection of data, I don't know, some measures of temperature for some period, for example. And it's able to get something out of it. So we see that in a higher dimension, there exists some structure in these points, and we can somehow extract it from that. Okay, so what about my very slow example? Maybe I will be able to show you something. Let's try to do with a Mobius strip. Well, it's a really complicated example. In a sense, you can put that into the plane, so you will always have some artifacts or some troubles with that. So let's wait for a moment. Maybe it will be able to show us something. I'm not sure why it works so slow, because previously it was more or less okay. Here we have it. So here is that strip. Once again, you see the structure of data with the colors. And here you see how the isomap is trying to put that into the plane. And here I have some notions. I'm afraid it takes too much time for each run, but please try at home. For example, the case of helicoid, it shows some difference between isomap and LOE, how they work. And you can try Swiss roll with isomap, for example, and different number of neighbors. So if I'm taking Swiss roll and I'm trying, for example, 10 neighbors, that should be some 1 result. Basically, I'm expecting some bad result because we have too low number of neighbors. And well, here it is. So it's something quite messed up. So here is the Swiss roll, and you see that 10 neighbors, it's like not very nice number. So, but if we are trying 15 neighbors, I expect that's the case. when it works more or less fine. So probably I have chosen these numbers to show you what happens when the number of neighbors is too low. And you see that manifold was somehow ragged. Here you see when the number of neighbors is more or less good. So here you see some structure in the data points. And what happens if you have maybe too many neighbors? And you can guess that we will be having the same troubles as with MDS, with original MDS, because we will be grabbing some points that should be lying somewhere far enough, and we won't have them far enough because we will have some parasitic connections. Okay, I guess it's still calculating. Yeah, so here we have it. So here we have glued together the things that we didn't want to glue together because we have too many neighbors. When we had 50 neighbors, we have got some more or less reasonable result. And for example, for 10 neighbors, you see that everything tears apart because you don't have enough neighbors to keep points together. So you are just getting some sort of holes into what you are calculating. So that's what we have. Okay. With that being said, what have we done today? So we have considered let's say, 3 methods of manifold learning. These methods are very helpful if we want to do, for example, visualization of data, because we cannot draw data that has more than 3 dimensions. So we should do something with that, and manifold learning can help us to squeeze that into 2 or 3 dimensions. So that's good. Noise filtering. If we are getting from higher dimensions to smaller dimensions, we can hope at least that we will get smaller noise into that reduced dimensional space. And of course, that will be useful for us in case if you want to perform feature extraction and engineering. So why not? I have some highly dimensional data. Some of my methods do not work on that data as I expect. But why can't I put the data through some sort of manifold learning method, get some smaller dimensional data, and maybe my different methods like SVMs or some trees or so on will work better on that data. So why not? We all know that the more dimensions we have, the worse our methods work. So that's the problem. Of course, manifold learning has its own problems that you should be aware of. So first of all, in manifold learning, there is no good framework for handling missing data. You can do something in PCA, but you can't do anything in manifold learning. In manifold learning, the presence of noise, it can short circuit the manifold and change the embedding. So that's the problem as well. So that's one of the questions. If we have, I don't know, some 2 parts of the manifolds, they are separated. But if you have some noise and some points are getting from one part to another close enough, you can get some parasitic connection, and this connection may spoil you the overall result. Because, for example, isomap that wasn't able to reach, for example, from one point to another through that parasitic connection, it will be able to get between points much quicker, and that will mess up the results. So yes, that may happen. That's the problem. And the manifold embedding its result is generally highly dependent on the number of neighbors chosen. So what I have shown to you, we change the number of neighbors and we get very different results. So you should choose somehow wisely that number of neighbors, maybe via cross-validation. So if you use some different method after that, if you are visualizing, maybe you will do that, I don't know, by hand, draw some pictures and look what happens. It's hard to determine the optimal number of output dimensions. So that's right. That's in contrast to PCA, because in case of PCA, we had some sort of notion of explained variance, and we were able to draw some, I don't know, some pictures with that explained variance, and we were able to tell, okay, I want to conserve, for example, 90% of variance. And that was okay. You can do that in case of manifold learning. So that's the problem, as well as the loss of the interpretability of your data, because PCA is just some sort of linear transformation. Of course, it's not very well for interpretability of your data, but it's much better than manifold learning that is some sort of, let's say, non-linear embedding that you get, and you don't even always know what was the function that is embedding your data from higher dimension to lower dimension. And of course, the computational expenses of the manifold learning, so it scales as big O from n squared. So that was the problem I showed you previously on the whiteboard. So if I have a number of points, I'm just searching for neighbors, I'll be forced to calculate all the distances between points to get all that distance matrix, and that's n squared. That's really bad. And in some cases, that will be even n cubed. So that depends on the method, and that's really bad. So you probably won't be able to work with really large data sets. While for the PCA, for example, there are some randomized approaches that may help you to avoid some large calculations. So that's what we have. So hopefully now you know at least some advantages of the manifold learning. We have seen some examples, and you know the problems that manifold learning has. So you will be having some idea when to use it and when not. And with that being said, if you have maybe any questions or comments, please.
Can we use, if we have, for example, depth of the photograph, manifold learning to unwrap the face to like so it like faces in front? If, for example, in photograph it looks right to the right side, and we like unwrapping like but not S shape or the Swiss roll shape, but shape of the face.
So you have some sort of three-dimensional model of the face, yeah?
For example, if I have photograph and the depth information, so yeah, like just like that.
So you have a photo and you have some sort of depth information. So you basically can transform pixels from your photo to the three-dimensional space. Yeah, you can probably try to unwrap that on a plane, but I'm not sure what you'll get out of it.
No, I'm expecting to get like the passport photo from any photo.
I'm not sure. So maybe if you want something like that, so maybe you will need some different approach, because photo on a passport, it's not like squeezed into the plane, but you have some sort of projection. So for example, in the pinhole model of camera, you are having 3D points and you are projecting them on the plane. But you see that distances between these points, they are not preserved as we are trying to do in manifold learning. For example, if I have a nose, so distance between the tip of the nose and my face, it may be quite large in 3D space. But when I'm looking straightly into the camera, you are seeing just some sort of projection, and you are seeing the tip of the nose and the rest of the face basically squashed together, let's say. Maybe it's better to employ some sort of 3D transformations and projection, because I'm not sure if you are willing to preserve all that distances. Because once again, if I'm trying to preserve distances, for example, I'm trying to preserve distance between the tip of the nose and the rest of the face, I'm not sure what will happen, how that will play out when I'm trying to squish that into the plane. So maybe that will, I don't know, somehow make a hole in the face and put the nose into the center or something like that. I'm not sure. So
okay. Probably projection is better.
Yeah, so I guess it's better to do projection, because I'm not sure if you really want to keep all that distances, because some big distances between some parts of the face, they don't look so in the photo when you are taking a projection. And when you are trying to unwrap everything on the plane, you'll be getting something quite, I don't know, interesting. So for example, you will have, I don't know, ears, not here, but somehow unwrapped in the plane. I'm not sure if that will look like you want. So probably not. That will more look like, I don't know, some sort of silicon mask just squished into the plane and somehow unwrapped. It will be more like that, but not like some living face in a photo. Okay, so any more questions, comments? Okay, if not, then have a nice weekend and probably see you on exam, or I don't know.